today is not Chapter 3, Section 5. It is Chapter 3, Section 6. One-to-one functions and inverse functions. Okay, so actually before we actually even turn the page and talk about what these functions are, okay, let's first think about kind of like a family of equations. Okay, so let's just start at the top. Starting at the top, we have equations that we are very familiar with. Okay, equations could be anything, right? And just for an example, all right. So an example of just simply an equation, and I'm going to make this an example that is an equation and not a function, would be x plus 1 squared plus y minus 4 squared is equal to 11. Okay, that is the equation of a circle. This is a circle. Dude, okay, all that looks terrible. As a matter of fact, hey, that kind of looks like Greek or something, doesn't it? All right, well, whatever. Circle. C-I-R-C-L-E. Okay. Okay, so this is an equation of a circle. Now, I chose a circle specifically because the next thing down from an equation that we have studied are functions. Are functions. Okay, and well, no need for an example there, I guess. All right, so functions are equations, but not all equations are functions. Okay, for instance, like this. Okay, my example is an equation, but it is not a function. Okay, remember a function pairs 1x to 1y. Okay, that's it. And remember, a function also passes that vertical line test. A circle obviously would not, right? All right. So today we're going to talk. We're going to go into a subfamily of functions. Okay. One of those subfamilies of functions is going to be a 1-to-1 function. Okay. And then a subfamily of a 1-to-1 function is going to be an inverse function. Okay. Oh, okay. That's awful. It's because again, I write small, and this thing just doesn't do small. An inverse function. Okay. So this is my tree of functions. Okay. You have the equation, and and functions are equations. Okay. One-to-one functions are a type of function, and inverse functions are a type of function. Okay. But again, this is just a tree of functions, right? But like this, a circle, I mean, unless you restrict a domain, will never be a function or a one-to-one function or an inverse function. Okay, so hopefully that didn't lose you too much. All right, I actually did read over this, and I kind of like it, but at the same time, I'm not going to read it verbatim. I'm gonna use our own cornbread language for this. Okay, so what we're talking about here, what the textbook is talking about here, is a need for an inverse function, or an idea of an inverse function, kind of. Okay, so we know that Fahrenheit and Celsius, they're different, right? And we also know that we have an equation for Fahrenheit and an equation for Celsius. Okay, kind of in the same vein. So if we want to figure out, if we want to go from Fahrenheit to Celsius, actually, what are they going to first? They're going from Celsius to Fahrenheit first, so we'll do that too. Okay, if you want to go from Celsius to Fahrenheit, okay, you have to use yeah, you have to use this function here. Okay, and then you can get your temperature in Fahrenheit. And if you want to go from Fahrenheit to Celsius, you would kind of do the inverse of it. You do the inverse, and you would use this function right here. Okay, and that's an example of inverse functions and how they operate. Okay. And again, I'm not going to read all that. It's a waste of time. You can read it. Here we go. Now let's get to the rigorous definitions. This I definitely will read. Okay, so a definition of a one-to-one function. A function f is one-to-one if for any values a not equal to b in the domain of f. Okay, so basically it's the x's, as long as the x's do not equal to one another, which that makes sense, right? Because if we compared f of 3 to f of 3, well, obviously they're going to be equal to each other, aren't they? Okay. Well, this is saying that if we took f of 3 and f of 9, something like that, okay, then when we take a function, right, we get a value back. We get a y value back. Remember? So we're saying that f of 3, if f of 3 is some y value, we're going to say y sub 1, okay? And if f of 9 is that exact same y value, y sub 1, then we are not a one-to-one function, okay? But if it were some other value, y sub 2, then it is one-to-one. So what is an example of that? Okay, well, let's take the function. Let's take the function f of x is equal to x squared. Okay, we know it's a function. It passes our vertical line test. We're very familiar with this function. We deal with quadratics until our eyes and nose and ears bleed, right? So we know it's a function. But it's not a one-to-one function, and here's why. If I take f of negative 2, that is exactly the same as f of 2, right? Because f of negative 2, well, if I plug in a negative 2 squared is 4. And if I take f of 2, well, f of 2 is also 4. Okay, so that's what this up here is trying to say, and what this is saying. Okay, but of course, we like to see numbers. We like to understand things from a different angle, and that's a different angle. Okay, excuse me. The alternative definition, a function f is one-to-one if for any two range values f of u and f of u equals f of v implies that u is equal to v. That is an okay alternate definition. It's saying that if we're going to have two separate values of x's, if we plug them in, then if we get both the y values, then those two x values are not different. Okay, they have the same value. But the raw definition up here, I think, is better, as well as my beautiful example over here. Okay, so that's what a one-to-one function is. Okay, it reads, the function sketched is one-to-one because any two distinct x values in a domain where a is not equal to b, and again, a and b, they are just x values. Okay, they could be anything. They could be negative 2 and 9, right? It doesn't matter. Okay, when the x values are not equal to one another, that's good. That's what we have. They're not equal to one another. The function values or ranges values are not equal to f of a is equal to f of b. Right? That makes sense, right? In no way would you have well, I guess it's okay explained, but realistically, this would be the better explanation, in my opinion, because instead of talking about what a one-to-one function is, let's talk about what it isn't, right? So it isn't this. So notice again, and this is an example of what I said with the x squared, right? We had a negative 2 and we had a positive 2, right? Well, if we look here, their y values are the exact same. So therefore, 25b, this figure here, is not a one-to-one function. Okay, so if your head hasn't exploded yet from one-to-one functions, I've got great news for you. Similar to a very easy eyeball test, to determine if something is a function, okay, we're going to have what's called a horizontal line test to determine if something is a one-to-one function, okay? And the same idea occurs here. So if we have if we talked about a normal function and we had a vertical line, okay, it's not working. We had a vertical line. Then if we cross that graph in more than one spot, then we know it's not a function. Good? All right. The horizontal line test operates the same way, okay? We're putting vertical lines through here. Notice that we don't cross anywhere more than once. Therefore, this is indeed a one-to-one function, okay? However, this graph is not, right? Because we are crossing all sorts. Down here, we cross 3 times, okay? So, horizontal line test, it is what it sounds like, and it's as easy as it looks. And I'm just going to go ahead and snip the solution and all that stuff because this is, I think, one of the easiest things that we do. All right, one moment, let me take a sip of coffee. Alrighty, excuse me. So, we'll just jump. Well, I guess we'll talk about the. No, we don't have to. We know what it is. We know what the definition is. We talked about it. Let's go to an example. Determine if each function is one-to-one. Again, I snipped the answers. Ooh, I didn't actually see C and D down there. I almost missed. Okay. So this would be where it helps to understand how to look at graphs. So we're gonna have to actually do C and D real quick. Okay. All right. So looking at A, we know that doesn't pass the vertical line test. That is not a one-to-one function, right? B is a one-to-one function if we look at it, okay? So graphically, it's pretty darn easy to tell what's a one-to-one function and what isn't, right? Well, we know A isn't and B is. So let's do. I mean, no. We'll just leave it. We'll leave it alone since we have our answers down here, okay? Well, C. If we first looked at C, we would say that is not a one-to-one function because it has an x squared in there, right? And we know x squareds, they look something like this and will not pass the vertical line test, right? Okay, but remember how we would restrict our domains, right? Remember that? If we restrict the domain to values that are only less than or equal to 0, then it is a one-to-one function, okay? So let's do a little bit of imagination. Okay, this is what we kind of brought ourselves into when I said, guys, you need to memorize parent functions, and then we do the transformations. Well, we're here now. Okay, so this is a quadratic function, x squared. Okay, so it's going to be a parabola, but this one's pretty easy. It's going to be a parabola shifted up 1 unit. Okay, so I feel like it's pretty easy to visualize, and I'm not even going to draw it. Okay, so imagine we have that parabola, and it's shifted up 1 unit on the y-axis. Okay, well now let's look at the domain there. Okay, we are restricting it to all values that are less than or equal to 0. So everything to the right side of that y-axis doesn't exist. And I'll go ahead and draw it. Even though I'm hoping some of you are thinking in your head right now, you don't have to draw it though. I can do this in my head. Okay. But anyways, so we know that this is a parabola, and it looks something like this. It's a parabola shifted up 1 unit, and again, the only values that exist are for values that are less than or equal to 0. So what we would do is we would erase that, and then we can tell it is indeed a one-to-one function. Okay, so C is a one-to-one function. B, I'll admit, B is a little bit harder to visualize. Okay, but that's okay, because it's more of a piecewise function, right? If it was set up like this, I think we'd be pretty good, right? As a matter of fact, if we just looked at this, right, we could say, okay, it's a line. Its y-intercept is at +4, so it's going to be shifted up, to like here somewhere. Well, here somewhere. and it has a slope of 2, so it's going to look something like this. Okay, uh, but then we have to combine it with 2x minus 6. Okay, well 2x minus 6, negative 6, that's down here somewhere. It has a slope of 2x, so it's also going to be shooting off. These are parallel lines, right? Okay, and so we would have to now determine or look at our um, domains. Okay, so what do these domains say? Okay, well, it says the first one is for all values that are less than or equal to -1. So, and those aren't parallel lines at all, are they? I'm sorry. So we would take all the values that are less than or equal to -1. So, everything here is not going to be there, and then maybe like this part. Okay, this isn't a precise graph at all. Hopefully the point gets driven home, though. We'll see. All right. And then the other one is for all values that are greater than or equal to +4. Yeah, we definitely needed a graphing utility for this. I do actually remember doing this in a class. Okay. I know it's not precise, okay, but we can tell that it is not a one-to-one function because we do end up crossing at more than one spot. So this might just be one that you could check out for yourself, put it in a calculator, and you can tell how it is not a one-to-one function. Okay. So like I said, yeah, the if we just have that nice little parent function with some transformations, a little bit easier. But then when we start to get to piecewise, we might need a graphing utility. Or we could just graph it more precisely, right? All right, so this reads, we are now ready to ask ourselves the question, why should we be concerned with one-to-one functions? Well, here's the answer. Every one-to-one function has an inverse function. So in order to have an inverse function, in order to have a function that, let's see, if we have, let's do this, f of, no, we'll do a, f of a into f of b. Okay. All right. So no, that's not good. Let's actually just go with the pace of the text. All right, so let's look at the definition of an inverse function. So let f be a one-to-one function. Okay, so notice how it's saying that f has got to be a one-to-one function. Okay, so again, one-to-one functions are inverse, have an inverse function. And again, this is where my little hierarchy of functions that I drew out earlier. Okay. So we let f be a one-to-one function with a domain A and range B. Okay. So then f inverse is the inverse function of f with domain B and range A. Furthermore, if f of A is equal to B, then f inverse of B is equal to A. So this is a lot to unpack. So let's get to the first thing that we kind of went along with in that definition. And so it's saying that f has domain A and range B. So let's go ahead and draw that out. So we're gonna do let's put this in blue. We're gonna have f. Okay, and then we're gonna have f inverse. Now, real quickly, as I write f inverse, in mathematics, that mathematics is such a humongous discipline that yes, we have to recycle some notation. Okay, an example of that would be if I just gave you this with no context, you might think it is either a point on a ground on a plane, or it might be the domain of a function from 3 to 5, not including 3 and not including 5. Okay, but when you get context, you'll know what I'm saying with parentheses 3 comma 5 parentheses. Okay, same thing with this. This -1 up here, okay, means inverse function. It is not following along with if we had x to the -1/2, that's just at 1 over x. Okay, it is not following along that path. We do not talk about inverse function notation the same way we would talk about negative exponents. Okay, so if you do that, you're going to be wrong 100% of the time. Okay, do not do that. We just have to recycle some notation, but context is key, or context is king. Uh, anyways, so f. Okay, let's say the domain. Actually, I don't have to put a sub f. The domain is going to be, we're going to call it a, and the range we're going to call it b. Okay, it doesn't matter what it is. I mean, the domain could be, heck, it could be 3 to 5, right? But we're just going to call it a for right now. Okay. Well, if the domain of the function is a and the range is b, then very easily we can tell you what the domain and range of the inverse functions are. Okay, because they are just opposites. The domain will be b, and the range will be a. Okay. The next thing that we have to unpack in this definition, it says, furthermore, if f of a is equal to b, then f inverse of b is equal to a. Okay. Well, they are functions that undo each other. Okay. So again, notice how if in our normal function, a maps to b. Okay. When I say maps to b, it could be 3. F of 3 goes to 7, right? A maps to b. Well, the inverse function basically undoes that. It'll map b to a, or 7 to 3. Okay, and again, we'll get better examples of this instead of the rigorous letters and words, right? Yeah, I'm not going to read that. I think I covered that pretty well. Same thing. Oh, I mean, it is the same thing, but let's actually snip this caution, because that is, I'm telling you, huge. We'll put it right there. No, let's put it down here. Put it out of the way a little bit. I'll let you really know. Okay, so there are a couple of ways to figure out if two functions are inverses of one another, right? And you need two functions to determine if they're inverses of one another. Okay, and in order to do that, we have to go back and use our composite functions that we did before. Okay, let's actually first start down here at the definition, and then we'll work up here at the examples. Okay, so the definition of composite cancellation equations. Now, guys, I mean, if you woke me up this morning and said, "Hey, what's that called?" I'm gonna be like, "Dude, I don't know. You just do it, right? You don't have to memorize that. It's just you just do it." Okay. So the composite cancellation equations. All right, what we're doing. All right, let's look here first. It is f of f inverse of x. Okay, we're just basically taking the composite like this. I don't know which notation you're more comfortable with, but these two are they're exactly the same thing. Okay. Let's do this. I like the idea of putting that down there. So we're gonna put the little arrow up here, pointing up here. Okay. So whatever notation you're more comfortable with, f of f inverse of x, of x is equal to x for all x in the domain, and then we go the opposite way. Okay, we go the opposite way. We're gonna do f inverse of f is equal to x. Okay, so what we're trying to do here is we're going to take the composite functions of both, and if in both occasions we get an x back, then those two functions are indeed inverses of one another. Okay, and so now let's get up here to the example, and then we'll do an example. Okay. Actually, that's not a good example at all, because we don't actually have an equation, do we? Okay. Well, let's look at it anyways. All right. If we take the f of f inverse of 8, okay, we do the arithmetic there. No, we're not going to do that, because I mean it does make sense. It just I know, again, as I've said plenty of times before, when I first took this course in college algebra, I wasn't going for math. Okay, so things like this, might not come as easy. Instead, what would be easier, right? Let's look at this real quick. All right, so if we have some function, okay, and we're just going to look here at this blue line here, okay? All right, so if we wanted to figure out what the inverse function looks like, okay? If we want to figure out what the inverse function of that blue line looks like without actually knowing what it is, then what we would do is we would simply draw an imaginary line here, right? And this line is y is equal to x. Okay, we talked about that as a parent function. That is the identity function. Okay, and all you have to do is mirror your function across that line. So if we took this blue line like this, and then we mirrored it across this line here, then we get this red line. Okay, so that's all it is to it. Same thing over here. So if we took this blue line, which looks like this, okay, and we mirrored it across the line y is equal to x, and then we get the red line. And that's how we just draw the inverse function. That's it. We just mirror it. Right, and this is an example of it. And so let's put it over here. I'm gonna draw it, and then I'm gonna snip the one from the textbook because I know it's always gonna be cleaner. Okay, so sketch the graph of f of x equal to x squared plus 1. All right, so x squared plus 1. Oh yeah, and our values have to be less than 0. Okay, so f of x squared plus 1 is going to look something like, that is a solid line. That's going to be something like this, right? Okay, but we are restricting the domain to only the values that are less than or equal to 0. Okay, so it looks something like this. All right, if we want to sketch the graph of the inverse, okay, so we're going to sketch the graph of the inverse. So we're going to have our imaginary line here, and therefore the inverse function is going to look something like, we're just mirroring over here, so we're going to look something like this. That was pretty easy, huh? That's how we sketch inverse functions. And of course, we have to set the domain and range too. Okay, so we'll talk about that as well. Okay, so it says also state the domain and range of f and f inverse of f. Okay, so f is going to be in red, okay, and f inverse is going to be in blue. Even though down here they're opposite. I should really look at that ahead of time, huh? All right, so the domain of f, it looks like it is from negative infinity to 0, right? Because, well, first of all, right here tells us that we cut it off for all values that are greater than 0. Okay, so the domain is going to be from negative infinity to 0, and then the range of f, okay, it looks like it's starting from here at 1, right? Because we shifted up 1 unit, and we're going all the way to infinity. So it looks like it's going to be from 1 to infinity. Okay. Now earlier, I said that if we have the domain and range of one of these, then we can easily say the domain and range of the other because they're just swaps, right? So that would mean that this would also be the range of f inverse, and this would also be the domain of f inverse. Okay, and of course we see that down here. Right. All you gotta do is just it's the exact opposite. Excuse me. And so if you think of inverse functions, that's how they're inverted. They're functions that are inverted. Okay, and that's about it for that. Okay, next up, Okay, here we go. Find the inverse function. Okay, so these 4 steps, actually 2x. This will be a perfect time to go back and show you how what we're about to do is a lot easier than what I tried to do a second ago. If I could just write things correctly, okay? So let's let's do the example and then we'll go back to that one. Okay, so this reads, we want to find the inverse function of f of x is equal to 2x over 1 minus 5x and state the domain and range, okay? Well, in order to find the inverse function, there is a 4-step process, very rigorous 4-step process, right? Number 1, the first step that we're going to do is we're going to change f of x to y, okay? So in doing that, we're going to have y is equal to 2x over 1 minus 5x, okay? All I do is change f of x to y. 2, we're going to interchange x and y, okay? So we're going to have x is equal to 2y over 1 minus 5y. Okay. 3, I think 3 should go up here. 3, we're going to solve for y. Okay. All right, so we're going to take that equation, we're going to solve for y. Let's put periods here, huh? So how do I solve for y here? Well, first thing I'm going to do is I'm going to multiply both sides by 1 minus 5y. So we're going to have x times 1 minus 5y is equal to 2y. Okay, and again, I'm just starting from here. Okay. All right, so next let's distribute that x through. So we're going to have x minus 5xy is equal to 2y. Right? We have to solve for y, so we need to put the y's on one side, okay? So what I'm going to do here is I'm going to we're going to add 5xy to both sides, okay? We could subtract 2y and stuff, but we're going to put all the y's on one side. We're going to put all the y's on the right side, okay? So we're going to do this. We're going to say x is equal to 2y plus 5xy. Perfect. Okay, and then again, all those things that we've done before that we don't use a lot, whenever we're learning new concepts, we have to recall those, right? And this being that we need to factor out a y from the right side. Okay, and then we're going to divide both sides by 2 plus 5x, so we're going to have all right, we solve for y. Okay, and then step 4, we're going to change y to f inverse of x. Okay, so I had x over 2 plus 5x is equal to y, so I'm going to change y to f inverse of x. So it's going to be f inverse of x is equal to x over 2 plus 5x. 2 plus 5x. Okay. Excuse me. And that's it. That is how we figure that out. One second. I just want to see how much we are. Oh, we didn't do a domain range. That's fine. We'll do it. I just want to see where we're at, so I can go back and do that one that I skipped over. Okay, we have plenty of time. Excuse me. Okay, so we wanted to find the inverse of the function and state the domain and range of f and f inverse of x. Okay, so let's look at the domain of f. Okay, so the domain of f is, all right, so we're going to be looking at our function f here. Okay, so if we take this function and we have to figure out the domain, okay, so we take the domain, well, then that is going to be all values not including 1/5. So how do I get that? Okay, well, again, if we take this function, 2x over 1 minus 5x, okay, then we know the denominator cannot be equal to 0, so it's just, simple algebra that we're used to. And then we get negative 5x is equal to negative 1, and then we get x is equal to 1/5, okay? So when x is equal to 1/5, then makes this denominator 0, and therefore that is the number that I cannot have in my domain, okay? So I cannot have x equal to 1/5, so I'll keep that up there as I write that. So that's going to be from negative infinity to 1/5 unioned with 1/5 to infinity. Okay. What about the range of f? Well, how do I figure out the range of f? I mean, just looking at it, we never learned how to find the range of f. I mean, if we graphed it, then maybe. Okay. But I got good news. We just have to use our brain. Instead, what we're going to do is we're going to find the domain of f inverse, okay? Because if the domain of f inverse is the same thing as the range of f, that takes care of that, doesn't it? Right? So with that said, I also know what the range of f inverse is. The range of f inverse is simply the domain of f. So that's going to be okay. So that took care of two birds, one stone. So next up, let's find the domain of f inverse. Okay, well, the domain of f inverse, well, this is f inverse. Okay, so all we have to do is take that denominator and equate it to 0. So it's going to be 2 plus 5x is equal to 0. So we're going to have x is equal to 2/5. Negative 2/5. Yeah, we'll just go slow. How about that? We'll have 5x is equal to negative 2. Yeah, x is equal to a negative 2/5. Okay, so x being negative 2/5 is what makes this denominator equal to 0. So therefore, I cannot use that in my domain. So my domain of my f inverse is going to be all the values except for negative 2/5. Okay, and then again, conveniently, that is the range of my f. Okay, and so that's how we did that. Now, let's go back to that previous problem. This one, okay? So we wanted to find, or we wanted to verify that they were inverse functions. All right. Now, the verification process is a lot easier if you actually write the problem down correctly. Pro tip. All right. But let's actually incorporate what we just learned, and we're going to go from f of x to g of x. Okay. So let us begin that. So step 1, we said we change f of x to y. So there we go. Good. All right. Step 2, actually, let's put that in blue. I like to stay consistent. So okay. Step 2, we said that we interchange x and y. So we're going to have x is equal to y over 2y plus 3. Good. And then step 3, we said that we solved for y. Okay, so we're going to multiply both sides by 2y plus 3. So we're going to have x 2y plus 3 is equal to y. Let's go ahead and distribute that x through. We're going to have 2xy plus 3x is equal to y. All right, same thing as the example that we did earlier, right? I can probably get one more line out of this. So we're going to subtract 2xy from both sides. So we're going to have 3x is equal to y minus 2xy. Okay, now let's go up here. And we're going to factor a y out of the right side. So we're going to have 3x is equal to, we're factoring a y out. So it's going to be 1 minus 2x. Okay. All right. And then we're going to divide both sides by 1 minus 2x. So we're going to have 3x over 1 minus 2x. That's equal to y. And then step 4, we said we're going to change y to f inverse of x. So f inverse of x is equal to 3x over 1 minus 2x. Okay, and this is that. Okay, so that's how we did it. Right? Again, 1, 2, 3, 4. We just follow those steps, and of course, I said this is f inverse of x, but we know that f inverse of x is also in this particular problem called g of x. Okay, so there's that. Okay, we're going to find the inverse function again. Okay, so this reads, find the inverse function of f of x is equal to x squared plus 1, and the domain is for all values of x that is less than or equal to 0. So let me get another sip of coffee before I do this one. Excuse me. I don't know about you guys, but man, I've been staying up late with this election garbage, and I'm feeling pretty woozy right now. So let's begin. Find the inverse function f of x is equal to x squared plus 1 for x is for all values of x less than 0. Okay, so step 1, we're going to change f of x to y. Okay, and we're going to put step 2 over here. Step 2, we're going to interchange x and y, so we're going to have x is equal to y squared plus 1. Okay. Step 3, oh, that's not hard actually. Okay, so step 3, we need to solve for y. So let's go ahead and subtract 1 from both sides. And then we're going to take the square root of both sides. So we're going to have, and let's go ahead and swap these sides again, because I really do like my y's on the left, okay, especially if I'm going to be doing this this operation I'm about to do. Okay, so I'm going to take the square root of both sides, so I'll have y is equal to plus or minus the square root of x minus 1. Okay, so I've got two different solutions here, right? Oh well, okay. Let's go ahead and do step 4, I guess. So step 4, we'll put down here. It's only one thing, right? We're gonna write f inverse of x is equal to plus or minus the square root of x minus 1. Okay, so how do I know which one of these? Okay, because again, I have two of them, right? I have the plus the square root, and I've also got the minus the square root. I've got two of them. Which one how do I know which one is which? Okay, well, if we look at the domain of f, okay, the domain we said was for all values of x that are less than or equal to 0. Okay, That if that's the domain of f, then we know that is the range of f inverse. Okay? So we're going to be using the negative of it, the negative value, just like that. All right. Was that it? We just had to find the inverse function. Didn't want anything else. Okay, so they didn't want anything else, but it looks like we're also going to be graphing it, or it's just showing it. So actually, we already did the graph. That's why. Yeah, we graphed it earlier in an example, so we don't talk about that again. Okay. Instead, we'll talk about the inverse function summary. Actually, we won't talk about it, but it will be on the notes. Okay. Anyways, that does conclude today's lecture.